Welcome to lesson 9 of non-Euclidean geometry. In this lesson, we're going to talk about something called trilaterals. They're sort of like a triangle where two of the sides have infinite length, and they also have some of the same properties as triangles do. If we consider two boundary rays associated with a boundary parallel in the same direction, so in other words, there are two rays that are parallel to each other, and a transversal segment, we get something called a trilateral. I have a picture of that here. So we have the two boundary rays going in the same direction, and we have a transversal, this line AB. Then these three things, these three sides, the outer side here, this outer side, and this what's called the inner side make up what's called a trilateral. And then we have some additional terminology. The interior angles here at A and B are known as the interior angles of the trilateral. And then this angle here, gamma, is an exterior angle. We have another one up here. I didn't draw it, but there'd be a second exterior angle here. And the triangle itself is referred to as trilateral CABD, and it has some similar properties in general to a hyperbolic triangle, which I've noted here. So trilaterals have three sides, the two outer sides and the inner side. And two of the sides are infinite in length, so that's where we're different from a hyperbolic triangle. The angles of a trilateral add to less than 180. We proved that in theorem 37 in using different terminology, but we proved these two inner angles here add up to less than 180. And then a line which subdivides the an angle of a trilateral. So I'm showing one here where you have a line subdividing this angle at A. It meets the other side, it intersects the other side here. And that was something we proved in theorem 32. For triangles, if a line intersects one side and does not intersect any of the vertices of the triangle, the line must intersect another side. With an additional condition, which we'll mention in this theorem, the same is true for trilaterals. A line which intersects one side of a trilateral and does not intersect any vertices will intersect another side of a trilateral, provided that the line is not a boundary parallel to either of the outer sides. So there's two cases. Our line in question either intersects an outer side or an inner side. We'll take the case where it intersects an outer side first. So let our line L intersect an outer side, let's say AC, at some point P. Then we have two subcases. Either L subdivides the angle APB, or it subdivides the angle BPC. In the first case, we know that L has to intersect AB. That's just a property of triangles. And in the second case, here, we know that L has to intersect BD, and that follows from theorem 32. In the second case, the line in question intersects an inner side, or the inner side, I should say, at some point Q. And then again, we have two subcases. But first, let M be the boundary parallel to AC through point Q. So that line here. By theorem 36, M is also a boundary parallel to BD. Remember, that was the transitive property we talked about in the last lesson. By hypothesis, line L is not a boundary parallel to either outer side of the trilateral, and thus distinct from M. So L either divides AQE or BQE. If L subdivides AQE, then by theorem 32 it intersects AC, and if it subdivides PQE, then by the same theorem, it must intersect the line BD. So in all cases, we have a line intersecting one of the sides of our trilateral, and it always intersects another side, unless it's boundary parallel, which we've stipulated it is not in the theorem. The following theorem concerns the exterior angle of a trilateral. The result is similar to that we have for triangles. In a trilateral, an exterior angle is greater than the opposite interior angle. So in other words, in our figure here, the theorem is claiming that gamma is greater than alpha. Since AB is a straight line, we know that beta plus gamma equals 180 degrees. We also know that the sum of the angles of a trilateral is less than 180 degrees, so alpha plus beta is less than 180, which means that beta plus gamma is greater than alpha plus beta. So we have this, and then we just subtract beta from each side, and we have the gamma is greater than alpha. Gamma is greater than alpha, which proves our theorem. We can also define congruence for trilaterals. Two trilaterals are congruent if the angles and middle side of one are equal to in measure to the angles and middle side of another. When I say angles, I mean the inner angles. This is the basically the side angle side congruence principle for trilaterals. We have two more theorems that hold true for trilaterals, but not necessarily for triangles. The first one I have listed here, and I'll prove it on the next slide. If an angle and the middle side of one trilateral, and again the angle we're referring to is the inner angle, are equal to the angle and the middle side of another trilateral, then the two trilaterals are congruent. Let's prove the theorem stated on the previous slide. So we have two trilaterals, CABD and GEFH, and they're such that the middle side AB is equal to EF in length, and that the angles A, here the inner angle at A equals the inner angle at E. We want to show that the two trilaterals are congruent by our definition, so we need to show that the inner angle at B is equal to the inner angle at F, and then we're done. And we'll do that by contradiction. So without loss of generality, let's assume B, the angle of B, is of measure greater than F. Choose a point J on AC, see here, such that ABJ is equal to the angle here at F, and choose J prime on EG such that AJ, this length here, AJ, is equal to EJ prime. And then focus on this triangle and this triangle here. By the triangle side angle side principle, ABJ is congruent to EFJ prime because of the side angle side. We can see that we have an angle here, a side, and another side, an angle, side, another side that are equal. And so that implies that ABJ is equal to EFJ prime. However, ABJ also equals F, the angle at F, right? That was what we constructed here. And so that means that F is equal to EFJ. So this entire angle here is equal to EFJ. But that implies that FJ coincides, so this line here coincides with FH, but that can't be since we explicitly put G prime on EG. So we have a contradiction, which means that B our assumption here, angle of B greater than the angle of F, is false. And if we had assumed B was less than F, we could have derived a similar contradiction. Therefore, we conclude that the angle at B, the inner angle at B, is equal to the inner angle at F. And then from what we were given up here, the two middle sides are equal, and A, the inner angle at A is equal to the inner angle at E. We know that the two trilaterals, CABD and GEFH, are congruent by our definition of congruence for trilaterals. So that's our proof. We have one more theorem in this lesson. It's another congruence theorem related to trilaterals. And it says if the corresponding interior angles of one trilateral are equal to those of another, then the two trilaterals are congruent. So we have two trilaterals here, CABD and GEFH, and we're given that A is equal to E in measure, and B is equal to F in measure. And in order to prove that the two trilaterals are congruent by side angle side, by our definition of congruence for trilaterals, we need to show that AB is equal to EF. So we'll again do this proof by contradiction. Let's assume that AB is bigger in length than EF. Select the point J on AB, shown here, such that AJ equals EF, and let the line JK be the boundary parallel to BD through point J. So this is a boundary parallel to BD. By theorem 40, CAJK is congruent to GEFH. So that's by angle side. That's what we proved in the last slide. And so we have congruence there. And then since these two trilaterals are congruent, we have that angle AJK is equal to angle EFH. Further, AJK is an exterior angle to this trilateral here, KJBD. And we know from a previous theorem an exterior angle is greater than the opposite angle here, which would be this angle over here. However, we have that AJK equals EFH. That's how we constructed it here. But EFH equals ABD. And so the exterior angle to the trilateral is equal to the opposite interior angle of the same trilateral. And that's a contradiction to theorem 39. Thus, we have our assumption here that AB is greater than EF is false. And if we had assumed AB was less than EF, we could have just flipped the argument around and also got a contradiction. And therefore, AB equals EF in length. And so by side, angle, these two trilaterals, CABD and GEFH, are congruent.